me if I'm annoying you or getting too simple or too complicated. But as most people know, this is the normal distribution, sometimes called the bell curve. I think the proper name would be the Gaussian one. And it has a rather nice property that it has an average, which in most cases when something is distributed according to the Gaussian distribution, you have something happening around there, more rarely out in the tails. You can have different averages, like these different curves, and you can have different levels of variance. The normal distribution is called normal because it shows up almost everywhere. And this is because it has a very interesting property. It's a so-called stable distribution. If you take random numbers generated from some probability distribution, which might be almost an even one, and add them together, you tend to get a normal distribution. Here I did a little hand wave because almost any distribution is actually not true. It has to have an average and it has to have a finite variance. But that's true for most stuff. If I took your shoe sizes and your ages and your weights and the last two numbers on your credit card and added them together, we would get some kind of random number which would be roughly normally distributed. Most would be near an average and there would be a few outliers. If we did this with everybody in London, we would get an even nicer distribution. So in general, as you get more data, everything starts to approximate the normal distribution very nicely. And this can of course be used to estimate a lot of things. So for example, the classical example is of course in games. If you're playing a game, what's the chance of getting a result that's very high or very low? Well, if you use dice that produce something like a normal distribution, you can make this estimation. You can of course use this in finance, thinking about, well, what's the chance of a fluctuation that's going to be bigger than the amount of money we actually got, and you can get an estimate and think about how much money you need to retain for that. And similarly in medicine, well, we know that most traits in a human tend to be distributed roughly in a normal way. What's the chance of something is going to be far out when it's actually all okay, but just by random chance we get an extreme case. So there is an awful lot of probability theory built on normal distribution because we got these wonderful properties. It turns out that you can add together stuff that even have different probability distribution and you still get a normal distribution. Except, of course, as we probably noticed the last few months on the stock market, that it's not always true that everything turns into nice normal distribution. So this is the returns on the Dow Jones, I think. And if you just plot them, it looks very, very normal. But if you use a bit of a more careful statistical test, if it was perfectly normal, it would follow this line straight. And it does, close to the center. But the tails, the extremely higher returns or the extremely low ones, deviate quite a bit. You get a few more high returns than you would expect if it was normally distributed, and you get a few more low returns. This is problematic. It's not something economists have been unaware of. Benoit Mandelbrot, the guy with the fractals, he was actually writing about this in the 70s. It's been in the academic theory and even in practice for quite a long time. People have been using it a lot. The problem turned out to be that it's pretty hard to actually control stuff which is not quite normal. So the problem of long tails or fat tails is simply that sometimes you get very extreme outcomes, and they occur much more often than you would think when you look at the middle part of the distribution. It turns out that that thing about the normal distribution being stable is true for another set of distributions, the power laws. And here is another, by the way, here's another good example of these weird outliers. So this is about freak waves on the ocean. Most waves are within this range and occasionally get something that's at least 3 times as big, which is very bad if you happen to be on a ship meeting that wave. Sailors have been telling stories about these giant waves for ages, and most people have been regarding that as just sailors' tales. Until we finally got sufficiently good measuring device, we could actually see that, oh, they actually do crop up for some as yet unknown reason. It seems to be a bit like random interference, suddenly getting a lot of waves to cohere into the right way to produce a very big, brief, nasty wave, which is, of course, then not seen again. And the problem is, this is very bad if you're always on a ship or on an oil platform. So, as I was saying, the stable distribution, there is another group of distribution which are called the power laws. So essentially, this is the size of something random happening, this is probability. The exponential distribution, that's the blue one, is closely related to the normal distribution, falls off pretty rapidly. The power laws fall off less rapidly. This is a logarithmic scale. You can see here that this is 10 to the power of minus 10 probability, and well, the exponential gets there pretty early, while the other ones go on. They're also stable. If you actually add together power law stuff, they also become more and more powerful, except of course that, as you can see, the extreme outcomes really dominate. Occasionally get something very, very big.
So that's not just a smudge on the graph, there's actually a data point.
Yes, that's a data point. So this is 100,000 power law random numbers I just put together. And practically all of them are around here. And there is one which is about 4.7 million large. But most of them are close to 1. It's actually quite interesting. I have let me show you an animation. So this is a time series where you get power law distributed random events. This is the average. Most of the time, it's below average. And you get a little bit of a peak. And some of them can be pretty large. And the really interesting thing is that some of them can be very large. So the problem here is normally when we talk about stuff, we think about the average of it. But here the average is pretty useless actually, because yes, most stuff is happening down here, but what we really tend to care about tend to be these really extreme outcomes. Because if this is something like disasters or stock market losses, one of those stock market losses can really wipe us out. It actually turns out that in that the data set, so this, if you just sum them together and look at how much of a share is due to the different events, this is the share due to the largest event. Then that's the second largest, third largest, and this one, the rest. So that single event completely dominated everything. This is very different from a normal distribution. I wouldn't expect in my shoe number and credit card example that some of you would get a number which would be ridiculously high. That would be extremely odd. But if we think about the stock market losses or avalanches, you can get these very extreme cases. There is a trick you can use to see if something is power law, and that is you take all the data you got, sort them from the largest to the smallest, and then plot them on their sizes on a log-log picture. What happens is that you get a beautiful straight line. This is the really, really biggest one, the one that was 4.7 million. This is the second largest one, and then you get the vast majority down here. You can also turn it around after some mathematical work to calculate what's the probability of getting something bigger than this. So given the data we already got, we can actually make a plot. It actually looks exactly the same, this beautiful thing about power laws, and that's why everybody loves them so much. But you get this kind of straight line. It's pretty easy to calculate. One reason we should care about power laws is that they crop up in a lot of, this is how normal distributions look when you plot them like that, is that power laws crop up in a ridiculous number of weird places. It's very fun. It turns out, for example, that if we take the frequency of words, they follow a power law. So that tends to be used much more than any other word in the English language and so on. If we look at how much of the different proteins there are around, it's a degree, how many interactions a protein got, nodes on the internet, and so on and so on. And this is probably because power laws have a similar stable property like normal distribution. When you have certain power law distributed stuff going into an interaction with other power law distributed stuff, the result tends to be a power law. If you have something that's more well behaved, it would be tending to become normal instead. But there have been a tremendous amount of more or less useful research about why we get so much power law. I really recommend Didier Sornet's book about extreme events in physics. He got an entire chapter about different theories people have been throwing up about why the power laws are going on. And probably most of these explanations occur in different places. Probably not one reason why we get so many power laws.
What's the name of that book?
Extreme Events in Physics. His name is Didier Sornet. He's very interesting. He actually arrived at the singularity independently of Werner Vinci based on analyzing stock market data and applying his theories. But his concept of singularity is a kind of infinite number of stock market crashes. It's very interesting.